Okay, we're looking at exercise 5D, graphs of exponential functions. The equation f of x equaling a to the power of x is an example of an exponential function where a is a positive real number which is not equal to 1. That is, a is an element of the set of all real numbers which are positive, excluding the value of 1. So we can have a being greater than 0, but we can't have it equal to 1. Formal notation or functional notation, we have the function f. The domain can belong to any real number. The range will produce a value or a set of values that are part of the real number set. And the rule is f of x equaling a to the power of x, where a, as we explained before, is got to be greater than 0 but excludes 1. Just working through the example on the left hand side here, we have f of x equaling 2 to the power of x. So the base here is 2. You can see the basic shape produced looks like so. As x approaches negative infinity, so it moves out in this direction, the curve comes closer and closer to the x-axis, but it never reaches the x-axis. As x approaches positive infinity, as it moves towards the right, the graph increases exponentially. There's a horizontal asymptote at the line y equals 0. And let's look at a couple of these key points. When x is equal to 0, we substitute 0 into the rule, so we'll get 2 to the power of 0. Anything raised to the power of 0 is equal to 1, so we get the position 0, 1, and that's shown just through here. Likewise, if we substitute x equaling 1 into the rule, we'll get 2 to the power of 1. 2 to the power of 1 is equal to 2, and so we come up with the position 1, 2. You can see that being the case here in that second line. If we now consider a different base, base e. E is a special number, it's an irrational number. It's known as Euler's number, and it's approximately equal to 2.71. So keep that in mind when I explain this. You can see it has a similar type of behaviour to f of x equaling 2 to the power of x. We substitute x equaling 0, we get the position 0, 1, and if we substitute 1 for x, we'll get the position 1, e. We have two types of basic shape. We have an increasing exponential, and we'll have an increasing exponential as x gets larger, the value of y gets larger. This will be the case when the base is greater than 1. We'll have a decreasing exponential if the base is between 0 and 1. So a decreasing as x gets larger, the value of y gets smaller. Transformations. So basically with the transformations, it's not unlike what we've covered previously. If we look at the basic y equals a to the power of x and how that transforms to this general case, y equals capital A of base a to the power of k multiplied by x plus b plus some constant, then we can see the effect here. The effect of capital A. This will be dilated by a factor of the magnitude of a, so we ignore the sign here, we just look at the size of it, parallel with the y-axis. That is, it's from the x-axis. So in other words, we take every y value and we multiply it by the size of capital A. Notice that if a is less than 0, then the graph will be reflected in the x-axis, and we've learned about that behaviour before. The coefficient of x, what's the effect of the coefficient of x, the value before the x, this k? In this case, it will be dilated by a factor of 1 over the magnitude of k, parallel with the x-axis. That is, it's from the y-axis. So in other words, what happens here is that every x value will be multiplied by 1 over k. So if k, and also if k is less than 0, so if k is negative, then the graph will be reflected in the y-axis. We expect that. The effect of c, basically if c is positive, it shifts the entire graph up, so the whole graph is picked up and moved c units up along the y-axis. If c is less than 0, the whole graph is picked up and moved down along the y-axis. Horizontal translations. The best way of thinking about horizontal translations is to just take what's inside the bracket here, make it equal to 0, and then solve for x. If x ends up being positive, as an example, say positive 2, then that represents that the entire graph has been picked up and moved 2 units along the positive direction along the x-axis. So basically, take what is up here, make it equal to 0, and if it's positive, it moves towards the right. If it's negative, it moves towards the left by whatever x is equivalent to. Let's look at some examples of some dilation factors. So dilated from the x-axis, which is the same thing as along the y-axis. Consider this. If we have f of x equaling 2 to the x, that's our standard graph. And I've drawn that in here in blue. If we now consider dilating it by a factor of 3, so we've got a 3 out the front, so 3 times 2 to the power of x, the point 1, 2 will be transformed. It will be transformed to the point 1, comma, the magnitude of 3 times 2 to become 1, 6. So in other words, what's happened here is that every y value along that original blue curve has been multiplied by 3. And obviously that would change that shape. And in this case, we'd get the graph that's shown here in red, where everything has been multiplied by 3. The same thing would apply, or the same kind of reasoning would apply, if we decided to have a dilation factor of 4. And you can see the effect here of the 4. So just think about every y value that's on that original graph being multiplied by what the dilation factor is. If we now consider having a dilation factor that is different, a dilation factor of 1/4, this would mean that every y value would be multiplied by 1/4. So a point that's on the original f of x equaling 2 to the power of x is the point 1, 2. The x value would not change at all, but the y value would be multiplied by 1/4. And so 1/4 times it by 2, we get the point 1, 1/2. Now, not that it's shown in this graph, but obviously it would come down like something similar to this. Dilations from the y-axis, that is along the x-axis. So in other words, every x value is multiplied by 1 over the magnitude of k. General case, f of x equals 2 to the power of x, and the point 1, 2 lies on that curve. If f of x is equal to 2 to the power of x, then f of x equaling 2 to the power of 2x would see the point 1, 2, which belongs to the f of x equaling 2 to the x line, would now become the point 1 multiplied by 1 over 1/2, 2, and would end up with a point 1/2, 2. What about if the coefficient of x was 1/2? Well, this time we'd see the point 1, 2, the x value would be 1 multiplied by 1 over 1/2, 2, and we end up with the point 2, 2. So when we're doing these, it's important to try and think about a particular point and what the effect would be on that particular point. I can explain this again in class. Reflections, so reflections in the x-axis, this is where the big A value, the number right at the front, is less than 0. Basically what happens here is that we're reflected in the x-axis. So think of this as being as taking every y value and multiplying it by -1. So if we consider the line, or the curve, sorry, f of x equaling 3 multiplied by 2 to the power of x, and that being reflected in the x-axis, then all that happens is that we're putting a negative out the front, and we're multiplying the y value by -1. So the point 1, 6 would now be transformed to the position 1, -1 times 6, which is 1, reflected in the y-axis. So this is when we're looking at the coefficient of x being less than 0. So we can see the original graph here, y equals a to the x, and then that's for where a is greater than 1. But if we have a negative coefficient in front of the x, it will be reflected in this line here, y equals 0. So let's consider f of x equaling 2 to the power of 2x, and it being transformed into f of x equaling 2 to the power of negative 2x. Then a point 3, 64, this is a point which does lie on this equation. This point here will be transformed into negative 1 times 3, 64, and we'll end up producing the point negative 3, 64. I've just run out of space there, but please believe me, it says negative 3, 64. Vertical translations, these are a lot easier to handle. The effect of C, and of course, basically, if we consider the a standard graph here of y equaling 10 to the power of x, if we then have a vertical translation of 5 units down, then you can see that every y value has just been moved down by 5 units. And I think this diagram clearly describes what's happening there. Horizontal translation, if we consider a graph y equaling 2 to the power of x, you can see its position there. But then if we look at y equaling 2 to the power of x minus 3, so the whole power is x minus 3, you can see that what we've done is that we've moved 3 units in the positive direction along the x-axis. So we'll just simply pick this up, move it across, pick this point up, move it across, pick this point up, move it across, pick this point up, move it across. So we've taken that whole curve and we shifted it 3 units along in the positive direction along the x-axis. In this instance, if we've got a function f of x equaling 2 to the power of 3x minus 5, and we're comparing that to the original, or to a standard f of x equaling 2 to the power of x, then to work out the translation, all we need to do is take the power, which is 3x minus 5, let it equal to 0, solve for x, and you can see in this case it produces 5/3. That represents a translation of 5/3 of a unit in the positive direction along the x-axis. Thank you.